Today I built another vulnerable app that looks like this. I'm going to show you the project and some resources that you can use yourself to make your app more secure. Starting out, I had no idea what to build. I had two criteria. I wanted to use Rust.
Rewrite. I'm actually rewriting Windows to Rust.
And I needed to make it vulnerable. So I started researching the subject, which means I asked ChatGPT. Finally, after doing all that heavy lifting, I knew exactly what to build. I'm building a document manager that is vulnerable to path traversals. I will not be implementing authentication, so I will assume that I'm logged in. The document manager will have four main functions: upload, list, read, and export. A simplified architecture of the application would look something like this. The backend has four APIs for the four different functions we discussed earlier. One for uploading, one for reading, one for listing, and one for exporting. The frontend sends requests to the backend APIs based on the user's interaction in the UI. The communication between the frontend and the backend will be strictly HTTP due to that TLS will be out of scope for this project. Let us take a closer look at the list API. In order for the frontend to list the user's files, it sends a GET request with the user's path as parameters. The backend responds with a 200 OK status and returns the list of the files in text plain format. Now that we understand the project, we will take a closer look into what is a path traversal. We start off by looking at the file structure of the project. Within the root of the project, we have multiple different directories. We have the source directory, which contains all of our Rust files for the Rust project. We have a config directory, which just contains some config files. And we have an uploads directory, which will contain all of the different files throughout the file system. Alright, time for curl. Let's see which requests we can send to manipulate the API. And maybe get information we were never supposed to see. Assuming we're logged in as Rasmus, a normal request to the list endpoint returns all files inside Rasmus folder. This is exactly how the API was designed to work. So far, everything looks safe. But what if we try to go one step up? Can we access the parent directory? Let's find out. If we add a simple .. at the end of the request, the server blocks it. Good. But path traversals often hides behind encoding, so if we URL encode the ... sequence and bypass the naive checks, maybe the server won't notice. And it works. We've successfully performed a path traversal. We're no longer confined to Rasmus folder. We can now access the entire parent directory. Which means we can now read Greg's and Mark's files too, files we should never be allowed to access. But a real attacker wouldn't stop there. They'd keep going deeper and deeper to see how far into the file system they can get. And with one more step, we reach the root of the project. At this point, the attacker can explore the file system freely and start hunting for the most sensitive files. Two things immediately stand out: the config folder and the .env file. Both are common places where developers store secrets. So let's start with the .env file. It's usually the easiest one to test because it often sits directly in the project root and is simple to access. The list endpoint can't read the file, but if we switch to a GET request instead, there it is. We can read the .env file. Empty in this demo, but still accessible. Next, let's explore the config folder. Inside, we find a config file, a classic target. Alright, let's see if we could read that one and see what hides inside. And it contains a secret. This is exactly the type of information attackers are looking for. Configuration files often contain API keys, database credentials, and sometimes even cloud provider access keys. Using nothing but path traversal, the attacker sends a GET request and the system gives them an AWS access key in return. Cloud access keys are one of the most dangerous things a hacker can steal. With valid cloud credentials, an attacker can extract sensitive data from object storage, download database snapshots, pivot into other cloud services, or spin up compute instances to run persistent malicious workloads. So, what was the actual root cause? Our application was vulnerable because it lacked security controls at some very fundamental levels. But here's the real question: how do we know which controls to implement? When designing a product, we need to think about security early, but we also need the right resources that tell us how to secure it. This is where OWASP comes in. OWASP is a global non-profit dedicated to improving software security, and they provide a ton of practical, free resources for developers. And today, we're zooming in on one of the most important ones, ASVS. is a structured framework that tells you what security controls a modern application should have. So when we analyze a vulnerability like path traversal, ASVS helps us identify the specific controls we needed all along. Like, say, file path constructions, which protects against traversal. So if we want to stop a path traversal or secure a file upload API, we don't have to guess. ASVS gives us clear, actionable requirements that transform weaknesses into stronger, more predictable security behaviors. ASVS isn't theory, it's a practical checklist you can use today to build stronger, safer applications. Whether you're validating input, securing file paths, or designing an API, ASVS gives you the language, the structure, and the controls you need to avoid these mistakes in the first place. If you're serious about building secure software, start using these standards. They save time, they prevent vulnerabilities, and they make you a better engineer. Thanks for watching. I'll see you in the next one.